So now we're going to look at equations of motion using cylindrical coordinates. And in this approach, you have a particle following some path. And what we'll do, we'll define the situation with an r component in a theta direction, and then also in the z direction. So you'll end up having forces potentially on this particle, and those forces will also be in the a force, say, in the theta direction, a force potentially in the z direction, and a force in the r direction. So again, we'll sum forces and set them equal to mass times the acceleration. So we'll end up summing forces in the r direction. Let's actually make this a scalar coefficient and use a unit vector here for the direction. Plus, we'll sum forces in the theta direction. Plus, we'll sum forces in the z direction. And then we'll set that equal to mass times the acceleration in the r theta and z direction. So it's a little different about this than what we did with normal and tangential components, is we're actually allowing acceleration in all three spatial directions. But because of this extra added complexity, we are going to have a little bit of a twist when it comes to the geometry of what's going on with our problem. So here we have our origin with respect to our reference frame, and it's a horizontal line, or a datum line, let's think of it that way. And then our particle path is here, so the particle will move from here to, from this point to this point, and so that'll be a movement in the so we'll create a change in theta there. Now this particle can have, of course, a force on it, maybe that is causing this movement. And here's where we run into the issues with this approach, that our friction, things like friction, are usually tangent to the surface, and things like surfaces, if a particle is moving on a surface, are usually tangent or normal to the surface. So we need to deal with all these with inside using the geometry of these cylindrical coordinates. Well, one way we can deal with that problem is we can define extend this out, and this is our tangent line. So let's write tangent. So this is our radius that we're extending out, and that's not necessarily perpendicular, but we can find this angle here. Let's actually spin the angle this way. The angle psi between the radius and the tangent. So let's look at how we might do that. So if our particle is moving in space here, and we initially locate r to that. Then as we change a small amount of time, we'll have, say, a d theta increment of time change. Then our particle here in its new position will have moved, our particle in its new position will have moved some ds. We know we can represent this ds by two components here, this and this component. So this, of course, is a dr, change in a small incremental shift in r. This is the same distance r as the original distance here, and this is dr. So this then is relating ds and dr as we've done before. This is going to be r d theta, which evolves again from this idea of s equals r theta. When you hold s as a large constant, you can end up with ds equals r d theta. Now, we're interested in this tangent and geometrically relating our theta and r to that. And so what we're doing, extending from above, is we have, this is extending r out. We're interested in understanding what this psi angle is. So I drew a little triangle over here as d theta is, really small, gets smaller and smaller and smaller. Then this sort of triangular situation occurs where this is our tangent here. In red, I'm just going to leave the words out. And again, this will be dr, and this is r d theta. And of course, this angle here between the red and this dr is psi. So we can then recognize that the tangent of this psi equals opposite over adjacent r d theta over dr. And we can rewrite that as the tangent of psi equals r over dr over d theta slope. So the change in r with respect to theta, which we'll often get in these cylindrical problems, which we can often easily get in these cylindrical problems. And of course we'll have r, so we can always find this psi. So that's a way to relate things that occur on the tangent or normal to the path. Okay, let's look at this example. We have a can moving through a slot, and it has a mass of 0.5 kilograms. And it's pushed by an arm that spins around, and theta is defined here. And r is the distance between this point O and the can. The rate that, or the relationship between r and theta is r equals 0.1 theta. And theta dot is 4 rads per second. It's constant. We want to find the force the arm exerts on the can. So let's draw our free body diagrams. First off, if we're going to do this in cylindrical coordinates, let's define those. We'll have mass times acceleration in the r direction this way, and then we'll go perpendicular to that, mass times the acceleration in the theta direction this way. Now, what do we have going on here? Well, we have the force of the arm pushing that, and that's vertical. And then, kind of, this is indeterminate. Again, we have our normal force here. Now, you might wonder what side the normal force is on, just pick a direction for your normal force and plug it in here, and we'll see what happens. So this then makes some angle, which we'll call phi, to the horizontal. Now let's relate that to that phi to our theta directions, and we'll do that again with the psi value that we did relating to the tangent. So this is our curve doing something like this, and then we have our tangent to the curve, and this is the direction that our this is what is the normal comes off of. So we defined then this angle here as phi, which is the same as this angle here, phi. And so phi is, this is still, I'm calling it theta. This is phi. Now, as we just discussed, this angle here we define as our psi angle, and the tangent of that we said is equal to r over dr d theta. So we have a function for r equals 0.1 theta, so 0.1 theta divided by the derivative of that with respect to theta is 0.1, so 0.1 over 1 is theta. So this is just theta. So now we're looking at a situation where theta goes from 0 to pi here. So this will result in then the tangent of psi equals pi. And the arctangent of that is 72.3 degrees. So 90 minus 72.3 degrees equals this phi, and that means that phi equals 17.7 degrees. So we look at this situation here. We can sum forces in the r direction, and we see that n times the adjacent over cosine of phi, and that equals our mass. Notice, since there is no weight in this problem, because this is horizontal plane, it does not come into play. But again, summing forces in the r direction, we get our mass, which is 0.5 times the acceleration in the r direction. And if we sum forces in our theta direction, we end up with F. And that's going to be that's actually in the direction of our acceleration here that we're defining as positive. I guess I should actually, just to be extra clear, these are the directions we're talking about. So F, and then we have minus n sine of phi equals 0.5 times the acceleration in the theta direction. So for our kinematics, we can set this up for theta and r, and then solving for the radial acceleration and the acceleration in the theta direction, we end up with these two values. We can plug those into the yellow equations above, and we get these results. Now, notice that our normal force is minus 2.64. That means we have it in the wrong direction. So it's actually touching the outside wall. But either way, we would have determined this in the sign. We would have determined whether we had n drawn correctly by how our sign turned out.